Hi, I'm Brian Shalloway. I'm a data scientist within NetApp's WWFCO data science practice. So I've worked mostly in sales and support problems. And my presentation today comes from some work I've been working on recently around pricing analysis, and I'll be discussing some simple methods you can use using regression, but some of the essential things you should know about using regression, and particularly things that are especially important in pricing contexts, in contexts where you are doing inference and really care about your coefficients and your estimates. So I first want to start by just acknowledging that pricing is hard. There's a lot of things that make it challenging. One is that you may have incomplete information. You may not know exactly what your competitors are selling for. There can be changing economic conditions, which I think is exemplified by this current moment that we're all in. There could be varying goals within the organization. At one point, a firm may be focused on expanding market share. At another point, they may be focused on maximizing profitability. There can also be competing motivations even within an organization. Sales reps may be willing to take a hit on margins in order to hit the quota, whereas leadership may be concerned about lowering prices and potential brand erosion that would come with that. You can also have very complicated products or configurations. So at NetApp, we're a large business-to-business organization, and we have a wide range of products, and those can have very different kinds of configurations associated with them that adds complexity to how you do pricing. And then there's also a variety of different sophisticated methods you can use. And I'm going to actually pause here and just make a plug for Stephen Kimmel and I will be leading a pricing strategy optimization study group. So our previous sessions have been more machine learning or statistical computing oriented study groups. This one's going to be around pricing strategy specifically. But today I don't want to talk about some of these more sophisticated methods and then also rely on a lot of those other pieces of information. I want to just start by saying, start with the analysis, start your analysis with what you have. And typically, organizations have historical transaction data available to them. They'll have information on their deals. And with this, you can still answer many questions, and it can provide a good starting place for future analysis that you might do. So the idea with regression, and that I'll be talking about today, is basically the concept that you can build a model that contains the components of your product. So in the context of pricing, this has some big assumptions with it. So one is that the value of the components can be aggregated, so either by adding together or multiplying together to get the total value of your total product that you're selling. Another is that actually know those components that add value to the product, and then you can represent these with a model. And in our case, I'll be talking about a linear model. The data for the examples I'll be going through comes from the Ames housing dataset. So there's some reasons why the Ames housing dataset isn't a perfect analog to like a business-to-business selling scenario. One of which is that there's no repeat business when in home prices. But the reason I'm using it is that houses, like often business-to-business selling, represents maybe large, complicated products. So in our case, you may have some sale price, and then you have a variety of components associated with the sale. So when doing this analysis, one of the first things you want to do is get your data into this form where you have the thing that you're interested in predicting is in one column, and then the associated attributes are in the others. And then you have now each individual row then is representing an individual observation for yourself. So each row in this case represents an individual home. In another case, you might think of each individual row representing an individual sale, or some other, depending on what level of analysis you're doing. But you wanted to have it organized where each observation represents a meaningful, is represented by an individual row, typically. What you get from from using regression to build a model like this. So in this case, I'm just building a really simple regression model incorporating living area, which essentially represents square footage, number of bathrooms, and garage area. And what you get is you have these coefficients attached to each of them. And in this context, you're thinking of these coefficients as representing the value associated with a unit increase of that component. So when you have these coefficients, then this can actually be valuable. You can use the coefficients themselves for, first of all, just understanding the factors and trends in your organization. So factors, what is important for sale price, And then trends, let's say you're building models across different periods. You can then evaluate how these coefficients are changing, so representing how potentially how value is shifting. And then you can use this also to make strategic decisions. So just pretend in this context that you're a home builder and you're looking at two different homes, and you have an idea of roughly how much it would cost to have some part of the house be a bathroom. And you can compare the cost of that to how much that bathroom is valued when it's actually being sold. So that's, you can compare, let's say it costs you $15,000 to convert this location to a bathroom, and you trust whatever regression model you built that tells you that that component's going to add roughly $12,000 of value. Then that would have you, reevaluate that decision. So it can be helpful for making strategic decisions in production. You can also then use predictions from a model like this also for, let's say, identifying outliers. So maybe there's you can see which deals were outside of what would have been expected, or you could also use it for providing pricing guidance on future deals that come in. When you're doing inference on the coefficients themselves, because you think that the value of the coefficient represents the value of a component of your product, it's important to understand the different meanings that these coefficients can have, as well as the behavior that they can have under certain conditions. So for the rest of this talk, I'm going to be just going through a few examples of this. So first is, let's discuss coefficient meaning and how that can change depending on the transformations that you do on your underlying data. So there's a variety of reasons you may want to transform your data. One, and the most important reason I think, is just to get a better model fit. You want to capture whatever pattern exists, and sometimes transformations can help you to better capture the relationship between, in this case, your sale price and the other underlying input variables. You also may be doing transformations in order to fit model assumptions. So some models have some assumptions associated with them, and sometimes you may need to transform your data in order to help fit those so that your optimization procedure can work essentially, or work better. Another reason is you may want to transform your underlying data in order to make your coefficients more interpretable in some way. So just going through a few of the common transformations. So the log transform is probably the most commonly talked about one. And when you log transform your data, it basically changes it from being a discussion of a unit increase to now being about a percentage increase or change. Sometimes you may also standardize your data. An advantage with that is that it can then put all of your coefficients on the same scale. So if you're using an optimization method that requires your data being all on the same scale, that can be valued in those situations. It can also be helpful for then being able to compare your coefficients more directly, just for interpretation purposes. Also, then there's interactions. So let's say the impact, just pretend that the impact of bathroom on sale price depends on the size of the house. In that case, that suggests there may be an interaction between this GR living area and bathrooms. So you'd want to create some other variable that can represent that. In related interactions, but there can also be change of degree. So say you have some nonlinear relationship or some complex dependency, generally that will show up with higher degree changes potentially. So this is just an overview of a few of the common different types of transformations you'll see. In the pricing context in particular, it's important to consider these because they shift a lot what that meaning is. And also, let's say you're in a scenario where it's kind of like it's ambiguous whether you need to transform your data or not. Maybe your model assumptions are fit, but you're kind of debating. There are costs associated with doing a transform. So maybe there may be advantages to be able to speak of, in this context, you may be advantageous to be able to speak of things in terms of change in dollars on sale price per unit increase in bathroom. So you may not want to take a log because that changes that interpretation in a way that doesn't fit your problem. Now, in general, I think it's best practice to do what you can to have the best fit to the model and have that be the guiding principle. But I think this is just important to understand in this pricing context, when you care about the meaning of these coefficients, that some of these things should be taken into account. Also important is to understand the assumptions that go with your model. And in addition to that is to understand the way that your coefficient estimates will be created depending on the optimization method that you're using and the relationship between your inputs. So if you're doing inference, you really need to consider your model assumptions, because if these are being violated, then that will reduce your confidence in the estimates themselves. And if you think of your coefficient estimates as representing the value of components of your product, you want to feel confident in those values. Also, it's really important to consider how the variables relate to one another, because that can impact how those coefficient estimates are going to be created. And depending on the method that you're using, this is also a source of potential instability. So I'm not going to talk about the model assumptions of ordinary least squared, which is the most common way of method for optimizing for linear regression. I will talk a little bit about this importance of considering the relationship between your variables. So let's consider a scenario where we're building a simple linear regression model using just total rooms. So total rooms in this case represents the number of rooms in the home other than bathrooms. So we're basically predicting sale price just based off of total rooms. So in this context, we see that as an increase of total room equates to a roughly $25,000 increase in sale price. Now though, let's consider building a regression model like the one we did beforehand, but now adding total rooms into that. And let's see what that coefficient on total rooms looks like. And what we see in this case is now it's actually negative. Before it was positive, now it's actually down to roughly negative $8,000. And you could think of this as representing essentially, now that we're taking into account these other variables, this coefficient estimate changes. So this, although there's a general association between larger rooms and a higher sale price, when you take into account these other variables, you see that there's actually a negative association with that value. In terms of like why this could be happening, it may be representing a genuine preference for larger spaces. So if you have two homes that are roughly identical, the home with fewer rooms is more valuable because it has more open spaces. Each room is larger. It also could represent confounding with year price, which isn't in the model. Maybe older homes tend to have smaller rooms, but have more of them, and then it's actually the older homes which is causing a confounding effect, and that's what's driving this negative coefficient on total rooms. So I mentioned the assumptions at the beginning, that you have the coefficients, that you have the factors that are impacting sale price. So this is an example of what's called like an omitted variable bias in your model. So those are potential things that could be causing this, but I actually don't want to go too far into that. What I want to note is that when you have variables that are highly related to each other, like in this context, all of these are going to be highly correlated with each other. Like they're all going to associate with just bigger homes across all dimensions. When you have this case, there's sometimes this kind of like general effect going on, and the coefficient estimates themselves, it's almost like a tug of war in terms of vying for influence. And when you have lots of highly related variables that this is going on with, it can create high degrees of variance in your estimates, which just means that slight changes in your underlying data can lead to big changes in your parameter estimates. So you may shift the data a little bit, and then suddenly your coefficients look way different, which if you care about your coefficient estimates, which we do in this context, you need to be thoughtful of. So there's some other optimization methods that can help to basically reduce the variance of your estimates. One thing you can do is use robust regression, which will make your estimates typically more robust to violations of those of the assumptions associated with ordinary least squares regression. Also more robust to influential points and outliers. You can also use Bayesian methods, which have more rigorous updating procedures and allow you to use priors to prevent the coefficients from kind of moving away as intensely as they might otherwise. You can also use regularization methods, which essentially add a penalty for having higher magnitude coefficients. So that's another way of kind of constraining the optimization problem in order to have behaviors that you prefer. It's helpful, though, to know that each of these will have different impacts in context when your input variables are related to one another. So, for example, if you compare lasso and ridge regression, if you have a set of inputs that are similar to each other in the context of lasso, what tends to happen is that it will pick kind of a surviving variable and then for the other variables, their coefficient estimates gets like pushed towards 0. In the case of ridge regression, what typically happens is that if you have a set of similar variable inputs, then their coefficient estimates are going to be kind of pushed towards a similar value. So these different optimization methods will have different influences under conditions when you have highly related variables that you're putting in your model, which if we care about our coefficient estimates, we need to be taking into account. So if you want to learn more about this, you can go to my site. I have a blog that is published there that goes in this a little bit in a little more detail and discusses some of those things around variance of coefficient estimates under different optimization procedures. Also, there I'll discuss. I'll be pushing out blogs in the next several weeks related to some other related ideas on this. So I'm, for example, building regression models across years and then comparing their coefficient estimates, or using the predictions and the likely intervals around those to identify cases that are outside the norm. So you can go to my website to read that blog, or you can follow me at Bershallow on Twitter, where I'll be almost certainly tweeting about it. So thank you.